In the context of the Stonesetch compactification of the natural numbers, beta n, a new partial order, tilde-wide, is defined on ultrafilters, derived from a divisibility relation on the natural numbers and extended to the space of ultrafilters. This order is explored, including its first omega levels, and introduces the concept of pattern for an ultrafilter, describing its basic divisors and their multiplicities. Patterns have a certain closure property in an appropriate topology, and the family of sets belonging to every ultrafilter with a given pattern is isolated. Every pattern with the closure property is realized by an ultrafilter. Ultrafilters and their properties are discussed, particularly in the context of nonstandard arithmetic. The nth level lane consists of ultrafilters that concentrate on the set lane equals P1 P2 Pn P1 P2 Pn element of P, where P is the set of prime ultrafilters. Basic ultrafilters, which are powers of primes pk, are introduced, and it is shown that every ultrafilter in L can be fragmented into basic ultrafilters. Non-standard extensions using superstructures are introduced to address the organization of ultrafilters into levels. A superstructure V, X, is a set containing a copy of N, and its non-standard extension is a pair V, Y, asterisk operator, where V, Y, is a superstructure with atoms Y superset equal X and asterisk operator. V, X, right pointing arrow V, Y, is a function satisfying the transfer principle. Examples of non-standard extensions are provided, including the fact that asterisk operator, N, equals, asterisk operator A, N and asterisk operator, A, N, equals, asterisk operator A, N. The connection between non-standard and ultrafilter extensions of N is established through the concept of generators, where for every X element of asterisk operator N, Tp, X, N, equals a subset equal N. X element of asterisk operator A is an ultrafilter. The authors highlight the importance of distinguishing between internal and external sets, where internal sets are those that belong to some asterisk operator A for a element of V, X. The internal definition principle is stated, which asserts that sets defined from internal sets are also internal. In the context of non-standard models of arithmetic, the internal cardinality of a set S is defined as the unique T such that an internal bijection exists between 1, 2, T, and S. A non-standard extension is C plus saturated if every family of internal sets with a finite intersection property is contained in a set of the form X element of N. X is less than or equal to Z, for Z element of asterisk operator N, N. This extension is assumed to be fixed throughout the discussion. The assumption of C plus saturation ensures that the monad of every ultrafilter is non-empty. It also implies a connection between divisibility relations and the ultrafilter's property of being a tilde-wide, minimal ultrafilter. The concept of internal sequences and their properties, such as the existence of a unique element X element of asterisk operator N for every internal sequence, is crucial. The product of ultrafilters F and G is a tilde-wide, minimal ultrafilter divisible by both F and G, but it may not contain all products X Y for X element of micro, F, and Y element of micro, G. The tensor product of ultrafilters F and G is defined as F circled times G equals S subset equal N. X element of N, Y element of N, X, Y, element of S, element of G, element of F. A pair, X, Y, is a tensor pair if, for every F, N right pointing arrow N, either asterisk operator F, Y, element of N or asterisk operator F, Y, greater than X. This property is essential for understanding the relationships between ultrafilters and their products. The authors establish that a hyperfinite set H has the finite intersection property, which is sufficient to show that BA, X, E, addio, / equals for all A in H, X element of G. This is achieved by demonstrating that X1 element of asterisk operator pi 1, asterisk operator A intersection, asterisk operator N times asterisk operator X, and Y element of asterisk operator X such that X1, Y, element of asterisk operator A, implying the existence of Y1 element of A intersection micro, G, with X1, Y1, element of micro, age. The authors then introduce the concept of prime ultrafilters, describing powers of prime ultrafilters. They show that for p element of p, all ultrafilters Tp, px, n, for x element of asterisk operator n are equals tilde operator equivalent. However, this need not hold for p element of asterisk operator p. The authors provide an example illustrating that consecutive powers px-1x and pxx are in the monads of equals tilde operator non-equivalent ultrafilters. The relation approximately equals p on micro, p times asterisk operator n is defined as p x approximately equals p q y if and only if Tp, px, n equals tilde operator Tp, qy, n. This relation is an equivalence relation, and its equivalence classes are denoted as EP. The authors introduce the concept of basic families of ultrafilters Pu equals Tp, px, n, p, x, element of u, for some p element of p and u element of EP, which are thought of as powers of p. The authors establish properties of these basic families, including that all elements of micro, Pu, are of the form px for some p, x, element of u, and that each up is either a singleton or a union of galaxies. A relation precedes p is defined on EP, where u precedes pv if and only if u, e, adio, / equals v and for some p element of micro, p, and some x, y element of asterisk operator n holds p, x, element of u, p, y, element of v, and x less than y. This relation is shown to be a strict linear order, and every increasing sequence in EP precedes p has a supremum, while every decreasing sequence has an infimum. The paper delves into the concept of ultrafilters and their properties, particularly focusing on the notions of well-ordered sequences and tensor pairs. It emphasizes the importance of understanding the U-topology on B and its relation to the standard topology on P, as well as the role of sets like A for a subset equal P. The discussion then shifts to the concept of patterns, which are functions tailored to represent the quantities of each basic divisor of an ultrafilter. A subset of these patterns, denoted as ACL, consists of U-closed patterns that satisfy a specific condition related to the sum of alpha, PV, over neighborhoods Q of a given ultrafilter U. The paper introduces a domination relation between two patterns alpha and beta, characterized by comparing their values on each prime ultrafilter P. This relation forms a partial order on A, and can be characterized using one-tune functions between certain sets related to alpha and beta. Several lemmas and theorems are presented, exploring properties of these patterns and their relationships. For instance, Theorem 3.3 states that for any x in N, P in P, and U, V in EP, X has either a finite number of exact divisors from union text U, precedence equal PW, precedence equal PV micro, PW, or an infinite number of such divisors. This result is crucial for understanding the structure of ultrafilters and their relationships with divisors. Examples and corollaries are also presented, illustrating how these concepts work in practice. For example, if alpha is U-closed and S is a subset of P, then the sum of alpha, Q, over all P in S is greater than or equal to N implies the sum of alpha, Q, over all Q in the U-closure of S is also greater than or equal to N. Similarly, if alpha is U-closed and A, bracketly, TV she less than gamma, A, bracketry, HT is a precedes pincreasing sequence in EP, then the sum of alpha, PV over all less than gamma implies the sum of alpha, Pu, over all U in EP is infinite. Overall, the paper presents a detailed analysis of patterns in ultrafilters, their properties, and relationships, providing insights into the structure and behavior of these mathematical objects. The summary begins by discussing the dominance relation between two functions beta and alpha, assuming beta dominates alpha. It considers two cases. If the sum of beta, PV, is finite, it defines a function g as desired. Otherwise, it constructs a sequence and defines g recursively. The proof then transitions to show that if a function fp exists as described, its cardinality is at most the sum of beta, PV. This leads into the concept of U-closed patterns and their properties, specifically Theorem 3.10, which states that every U-closed pattern is U-closed. The discussion continues with Lemma 3.11, demonstrating that if X is less than or equal to Y, then their patterns alpha X and alpha Y are comparable. Theorem 3.12 establishes that for any f and x in its domain, their patterns alpha X and alpha F are equal. This leads to the definition of alpha F for any f and the corollary that if f is similar to G, then their patterns are equal. The example section includes a note on the maximum of P in P and a discussion on the class max, concluding that f is in max if and only if every M divides f. The paper discusses the properties of ultrafilters in nonstandard analysis, focusing on the relationship between two types of patterns, alpha and beta. It introduces the concept of U-closedness for patterns, allowing a connection between these types of patterns. The authors prove a theorem stating that if alpha and beta are U-closed patterns with alpha preceding beta, there exists an ultrafilter G whose pattern alpha G is approximately equal to beta. They also provide an example illustrating the necessity of the U-closedness condition. A counterexample is presented to demonstrate that the theorem cannot be generalized without the U-closedness condition. The paper concludes with a corollary stating that for every U-closed pattern beta, there exists an ultrafilter G such that alpha G is approximately equal to beta. The authors delve into the concept of U-closed patterns and their relation to ultrafilter divisibility, providing insights into the properties and behaviors of these mathematical objects. They discuss self-divisibility and list several open questions for future investigation.